Okay, so now we'll talk about chapter 23 and go about induced induced EMF and magnetic flux, Lenz's law and Faraday's law of induction, motional EMF, and eddy currents and magnetic damping. And then talk briefly about, electric generators and back EMF. Okay, so induced EMF is when you have a changing magnetic field, and a changing magnetic field is going to induce a current caused by the changing magnetic field. So you get an electromotive force induced by a changing magnetic field, and it's done whether or not there's a physical connection. So for example, you have a battery here, and if you close the switch so the current flows through these loops of wire, it's going to generate a magnetic field, and then the magnetic field going through this loop of wire is going to cause a deflection when that battery is switched on. And you can see that you can also do it whether you have a current generating the magnetic field, as in this case, or you have an actual magnet, and as you push the magnet through the loop, it's going to generate a current, and you can read that on the galvanometer. So if you push the coil in or pull it out, notice that when the magnetic field is increasing up, you get a reading this way, and when the magnetic field is decreasing down, you get a deflection that way. Okay, and if you flip it around and south goes in, it's the same as a north decreasing, and pulling the south out is the same as a north increasing, and that's just because of the flow of the magnetic field goes from north to south. And then here's the important point: if the magnet is just sitting there and not being moved, you generate no EMF, no current. So you need the magnetic field to be changing. Okay, so the main concept for determining the EMF is to consider the magnetic flux. Okay, and magnetic flux is the amount of magnetic field, B, the strength, going through the area A, and the angle between the magnetic field and the current. Okay, so here's your area, your proto area. You've got magnetic field lines coming in at some angle theta, and the component you want is the vertical component, because that's the component that's actually going to do the EMF generation. So remember that if you've got a vector like this, it's made up of a horizontal and vertical component. That's what makes it come at that angle. So you've got a vertical and a horizontal, and that component there, VA cosine theta, is the total flux. Okay, so when you're trying to calculate the flux going through a surface, it's just the magnetic field strength, which is generally constant over that surface, times the area of the surface, and then the cosine of the angle between them. Okay. Generally, the magnetic field will be perpendicular to the surface, so the magnetic field will just be, the flux through the surface will just be BA without the cosine theta, because it'll just be the magnetic field times the flux. Okay, so Faraday's law of induction says that the EMF generated, because we know now that if you do push a magnet through a coil of wire, you're going to generate an EMF, but as physicists, you want to be able to calculate exactly how much. So the EMF you generate is simply the flux, or the change in flux, divided by the change in time. So if you push a magnet through the coil more slowly, you'll have less EMF than if you jam it through really quick. And then you'll notice that it depends on the number of turns or loops of wire. So if you have 1 loop, or 2 loop, or 3 loop, or 4 loop, or 5 loop, then if you have 5 loops, you're going to have 5 times the EMF generated when the magnetic field flows through it. Okay, so that's EMF right there, is just N times the change in flux over change in time. So what is change in flux? An example would be, let's say you keep the area constant. So flux is BA. So you're keeping the area constant, so then it'll be B final minus B initial times the area, okay? Because your flux is changing divided by the time it takes to make that change. Maybe 1 second, 2 seconds, 3 seconds, something like that. So BF minus BI times the area. So that's keeping the area constant, as is in the case here where you've got this loop of wire, and as the magnetic field goes through it, what's changing is simply the strength of the magnetic field. You're going from a weak area out here to a strong area here, so your magnetic field is increasing, and when you're doing that, your area of your coil is staying the same. Okay, so your EMF then is generated as the change in flux, change in time. Lenz's law says that when you push a magnet into a coil, the coil, there's going to be a current that is generated in the coil, and the question you have to ask yourself is which direction is the current generated? Is it going to be rotating clockwise or counterclockwise? So what these three diagrams are trying to show you is that you go from a weak field to a strong field, so you're increasing your magnetic field strength. The current is going to be generated in such a way so that the current is going to flow. If you do your right hand rule, which means you point your thumb in the direction of the current and your fingers loop around, and means that the magnetic field is going to be generated down through the coil. The magnetic field that's induced by the coil and the current that flows is going to be in such a way so that the magnetic field generated opposes the change that's currently happening. So if you're increasing the magnetic field this way, the current generated will be as if a magnetic field is induced down to oppose that motion, that change in magnetic field. So the same thing is true here. If you're pulling the magnet out, so you're going from a strong to a weak field, then the change is you're weakening the magnetic field, so that your right-hand rule says that the magnetic field induced by the coil should act to maintain that field, which means it's going to have to generate a field opposing the decrease. So it's decreasing this way, so it's going to generate a field that way. So it's a little bit confusing because what's actually happening is you've got one coil of wire and your magnet north-south. As you pull the magnet down, you're going to generate a current in the circuit. So the current's going to loop around. The question is, what direction is it going to loop? So let's say we're pulling the magnet down. We've got two magnetic fields to keep track of. The magnetic field from the actual magnet, but then as you pull the magnet down, you're actually going to generate a magnetic field which loops around the coil itself. Okay, so we got to keep track of those two magnetic fields. So that's what this is about. So as you pull the magnet down, the coil is going to, since the field's getting weaker, the field that it generates inside the coil is going to want to oppose that change. It's going to want to boost the signal back up. So you're pulling the magnet down, which means you're decreasing the strength of the magnetic field, and the coil is going to say, no, I want to hold on to that. So the current is going to have to be generated this direction, because you point your thumb in the direction of the current around, and your fingers are going to curl up around this and point up towards the center. Okay, and so that's the direction of the current there. So just make sure you're thinking about this in terms of you've got the magnetic field, the strength of the magnetic field here, but then you're also going to generate a magnetic field, which is like a current in a single, loop of wire or whatever. So just keep track of that. It's a little bit tricky. Okay, so here's an example. You can go through that. So motional EMF. So you have EMF is equal to N minus MD, or change in flux over change in time. And previously we looked at when you kept the area constant. So you have minus N, and then it ends up being B final minus B initial. But we're keeping the A the same over delta T. And why am I writing that? Because change in flux would be BA minus BA over delta T, and if this is our final and our initial and our area is the same, then you can just factor out the area and write it like that. Okay, but what if the area is not changing and the magnetic field stays the same? So now we have B being constant times A final minus A initial over delta T. So that's what this one is about. Our area we're actually increasing the area now. We're keeping the magnetic field the same, so all these little X's are telling us the magnetic field is constant going into the page, so into your screen. But our area is changing, and it's changing at a rate of change in X over change in T. So the area of the change is L delta X. So that means the flux is increasing because we're increasing the area. So our flux here, our change in flux, we're increasing the amount of magnetic field lines that can flow into it. The magnetic field is B, it's constant. The velocity is this way, so if you point your thumb in that direction, your fingers into the screen, because that's the direction of the magnetic field, then the force is going to be up. And that means that the current is going to flow around the loop, okay, that way. And that's using that right-hand rule to do that. But then, if the current is flowing this direction, you point your thumb in that direction, you use the second right-hand rule to show that the induced magnetic field by this motion opposes the field that's going into the page, and then the magnetic field generated by the closed loop here comes out of the page. Okay, so that's a really tricky thing to comprehend, but remember the EMF generated is equal to change in flux over change in time, and you can change the flux either by increasing or decreasing the strength of the magnetic field, or you can change it by changing the area of the loop. Okay, so this is a conductor, they're all in contact, you're sliding a metal rod along a rail, okay, and this is called motional EMF. So the change in area is the length times the delta x over delta t, and delta x over delta t is is velocity, so EMF generated is just BLV. Okay, so here's an example. You've got a tether on the space shuttle, and you're imagining the magnetic field in space there. And then the question is, what's the motional EMF generated between the satellite and the space shuttle? And they give you some things: the magnetic field strength, the length of the tether, and the velocity of the traveling, and you get 7,000 volts or something. Okay, so then if you take, an example of a piece of metal falling in a magnetic field, as it does that, you're going to get these little eddy currents showing up in the metal, and those eddy currents can generate a force too. And so here's an example. You've got a piece of metal falling into a magnetic field. You're causing a current to loop around in a circle like this, because you can do the right-hand rule. The velocity is this way, the magnetic field's into the page, so the force that it generates is going to be that way, and that actually causes the thing, as it falls, it'll end up right here and stop, because it's going to feel a force that opposes its motion, and that's these eddy currents do that. And if you put little slits in the metal, the eddy currents are very small, and the force that it generates to oppose its motion is very weak, and so it's a reduced effect than if it were a solid piece or a connected rod. Okay, so examples of this are in a scale. It slows down to help achieve the balance and counter out the wobble. If you have flowing bits of aluminum after you throw a trash away, the metal bits will slow down while everything else falls away. So you can separate metal out even if they're, not conductors. You've got a metal detector here. Okay, so electric generators. If you want to generate an EMF in a coil, you can just, rotate a coil, and that's what they're doing here. Rotate a loop of wire in a magnetic field, and that's changing your flux over your time, because you're changing the area in the magnetic field, and you're basically changing the cosine of the angle between the area and the magnetic field. So you're looping from 0 to 90 degrees, or, whatever. So you're going from -1 to 1, and then you can get your maximum loop here is N times area times B over delta T. Put all that in here to figure out your generation, your loop there. Another thing to consider is that, let me see. Yeah, okay, another thing to consider here is that as this thing turns, it's got a length, it's got W over 2, a width over 2, and as you rotate at a frequency omega, that's going to basically be a way to change the flux in a certain amount of time. So this omega then is just the frequency of your rotation, and so then you can get what's called the EMF induced in a generator is just NAB times omega, and NAB times omega gives you the peak EMF. Okay, and so that's just how these motors work. Okay, blah blah blah. So there's a couple different ways. As it rotates, you can get AC type thing, or you can only pull off the positive voltage if you want. So then your output is always, positive or something. So anyway, okay, back EMF happens because this coil, by its own nature, is going to generate a magnetic field opposing its motion too. So you have a back EMF. So as you turn a motor on, it uses the most current it's going to use, but then as it runs, the back EMF gets greater until it balances out. And so it's initially like when you turn a vacuum cleaner on, the lights might dim initially for a second, or when you click on your hair dryer, the lights might dim for a second, and that's because initially you have full current going into that motor, but once it starts spinning up to a max speed, it generates its own back EMF, which reduces its power consumption a little bit. So that's what back EMF is. You draw it here in this picture, and it's just the load that ends up reducing your amount of energy. Okay, so then we'll talk about transformers next time. Okay, bye.